Hi, I'm Clare Snyder. I'm a final year PhD student at Michigan Ross, and I am so thrilled to be sharing a quick overview of my paper, Algorithm Reliance Fast and Slow, which is a finalist in the Service Science Best Student Paper competition at Informs this year. The paper is joint work with my advisors, Sam Kepler and Steve Leiter. In the study, our focus is on worker behavior within personalized services. For example, we can think about a styling service like the one pictured here. There are two people involved in the service interaction. There's a human worker and a human customer. For the worker to make a good recommendation, he has to know something about the customer's needs or preferences. In this example, it might be that the customer loves green and going to the beach. With that information, the worker has to decide what option is going to make the customer more or less satisfied. Many companies are introducing decision support algorithms to help workers make these service decisions. It could be to help workers make higher quality decisions, and it could also be to help workers make faster decisions without sacrificing quality. In our research, we want to understand how workers, like the one pictured, use algorithms advice to provide personalized service to their customers. A key feature of the service context we study is that workers maintain decision authority, which is to say that they can deviate from their algorithm's advice. This raises the possibility that companies may not realize algorithms' potential benefits for quality or speed. In particular, we know from a large and emerging body of work that people are averse to using algorithms. They avoid using algorithms even when doing so would improve their decisions. However, most algorithm aversion research has happened in forecasting contexts. We know that contextual features there, like time pressure, can make people willing to use algorithms. People may be willing to use algorithms in different ways in service contexts. I specifically bring up time pressure here because we know time pressure is an important part of many service decisions. System loads from customer queues put pressure on workers to serve customers fast enough to keep those queues moving. Traditional service operations management research, which is about settings where there is just a worker and customers without an algorithm in the mix, tells us that workers tend to speed up as their system load increases. A consequence of the speed up is that in many cases, the quality of service suffers because of a speed-quality trade-off. It's less clear what's going to happen when we bring algorithms into the mix, because now time pressure could also affect workers' willingness to use the algorithm if we think service is similar to forecasting. This brings us to our research questions. First, how do workers engage with algorithmic decision support to manage system loads? Second, what are the implications of their behavior for system performance? And we answer these questions with an experiment. We use a 2x3 treatment design where one dimension varies system load, there's a high load and a low load, and the other dimension varies the algorithm. So some participants have no algorithm, this is our control. Some have a high quality algorithm we call the superior algorithm, and others have advice from a lower quality algorithm, the inferior algorithm. Participants don't actually know the quality of their algorithm's advice before they begin the task. You can see a diagram of the experimental task here. Participants in our experiment act as workers inside a service system that includes a customer queue. Their task is to provide joke recommendations to their customers as a stand-in for the kinds of personalized service decisions that exist in real life. Now, what you're seeing here is one of the important results from our experiment, which shows a scatter plot of participants' rating performance and throughput time performance in each of the 6 treatments. High load is HL, low load is LL, superior algorithm is SA, inferior algorithm is IA, and no algorithm is NA. And what we were struck by when we made the plot is that participants in the low load typically have very similar throughput time performances. People are a little bit faster with a superior algorithm than with no algorithm, but it doesn't really seem in general like giving someone an algorithm when there's a lower load does that much to their throughput times. In contrast, and I think you can see where I'm going here, when we look at the high load, there's a pretty similar pattern for the no algorithm and the inferior algorithm participants, but once we give participants a superior algorithm, it really starts to change, which takes us to the idea that, well, better algorithms improve throughput times a little, better algorithms plus high system loads improve throughput times a lot. The reason for the finding is that participants can use the algorithm in one of 2 ways. We see some participants follow the advice with deliberation, they're taking time. We see other participants are directly defaulting to the algorithm's advice without taking time. And we see that it really takes defaulting to the algorithm's advice to be faster than having no algorithm, and that's happening most in the high-low superior algorithm condition. And it's happening even more over time. So what you're seeing here is a graph showing participants' rates of following the algorithm in general and defaulting to the algorithm's advice in each of the 4 treatments where participants have advice from the algorithm. This brings me to the 2 takeaways I want to highlight. Algorithm reliance can be fast or slow depending on whether decision makers default to the algorithm or deliberate. And algorithm quality and system load are mutually reinforcing factors that influence both service quality and especially speed through that algorithm reliance behavior. There's a lot more in the paper, including a second study that looks at some interventions. If you do have any questions or want to chat, please reach out to me at claresnight@umich.edu. Thank you so much for watching our video.